Today, we're going to tackle one of the most powerful ideas in human history. But don't worry, we're doing it without all the scary math. We're going to build an intuitive map of motion, right from the ground up.
So let's start with a simple question, one that turns out to be a surprisingly deep puzzle. I mean, it stumped the greatest minds for centuries. Seriously, think about it. How fast are you moving at this very instant?
We all think we know what speed is, right? It's just distance over time. But here's where it gets weird. If you try to define speed at a single frozen moment, an instant, where time literally stands still, you run into a massive logical paradox.
Yeah, this is the absolute heart of the problem. In a single instant, no time passes, so the time is zero. And if no time passes, you haven't moved at all, so your distance is also zero. That means your speed is 0 divided by 0. And what on earth does that even mean? It's just undefined. It's a mathematical dead end.
And believe it or not, this isn't some new confusion. This goes all the way back to the ancient Greeks and Zeno's famous paradox you see on the left, with Achilles and the tortoise. The whole idea of slicing time into infinite little pieces made it seem like motion itself should be impossible. It even pops up in modern jokes, like the one about the driver who argues, "Officer, how can I be going 60 miles an hour? I've only been driving for 7 minutes."
So to solve this ancient puzzle, you couldn't just use the old math. A completely new kind of mathematics had to be invented, a language built from the ground up just to describe change itself.
The huge breakthrough came from two absolute giants of science, Isaac Newton and Gottfried Leibniz. Now, working totally independently, they didn't try to solve the impossible problem of dividing by zero. No, they were way smarter than that. They came up with a brilliant workaround.
They basically imagined looking at motion through an incredibly powerful magnifying glass. Instead of just setting the time to 0, they asked a much cleverer question. What happens as we make that little chunk of time smaller and smaller and smaller still? They watched to see what the ratio of distance to time approached as that interval got ridiculously infinitesimally close to 0. This powerful idea is what mathematicians call a limit. And this concept, this limit, gives us the precise mathematical tool we need. It doesn't calculate speed over 0 time. Instead, it lets us find the exact rate of change, the speed, at any single frozen instant we choose. And this amazing tool has a name. It's called the derivative. You could say it's the hero of our story. It's the elegant solution to that ancient paradox that finally lets us talk about instantaneous speed in a way that actually makes sense.
So here's the really crucial point. Velocity is now defined mathematically as the derivative of distance. When you see this notation, ds/dt, don't think of it as a normal fraction. It really represents that limit we were just talking about, that infinitesimally tiny change in distance, ds, over an infinitesimally tiny change in time, dt.
And this is where the magic happens. This shows you the real power of the derivative. If we have a formula for an object's position, like s equals 16t squared for a falling ball, calculus gives us a simple rule to turn that into a brand new formula for its velocity, v equals 32t. It's like a machine that takes an equation for where something is and spits out a new equation for how fast it's going.
Okay, but what's really interesting is that this whole process is a two-way street. If we can go from distance to speed, is there a way to go from speed back to distance?
Let's flip the problem around. Imagine you're in a car, but your odometer, the thing that tracks total distance, is broken. All you have is the speedometer. You know how fast you're going at every single moment. So how can you figure out how far you've actually gone?
Well, the idea is to break the whole journey down into tiny little slices of time. For each little slice, you multiply your speed by that tiny bit of time to get a tiny piece of distance. Now, as you can see on the left, if your time slices are big and chunky, your total is just a rough guess. But as you make those slices thinner and thinner and thinner, infinitesimally thin, like on the right, and then add them all up, your estimate becomes the perfect exact total distance. And this process, this idea of summing up an infinite number of tiny little pieces to find the whole, that's called integration. And the mathematical tool for doing it? That's the integral. It is the perfect other side of the calculus coin. And right here, you can see the beautiful symmetry of it all. The derivative is like a microscope. It zooms way in to break motion down and find the rate of change at one single instant. The integral, on the other hand, is like a telescope. It pans way out and builds everything back up to find the total accumulation over a stretch of time. But why stop there? We can apply the exact same logic one more time. What do you call the rate of change of velocity? Well, that's acceleration.
It's how fast your speed itself is changing. So the derivative of velocity gives us acceleration. It's the same tool, just used one level deeper.
And just like that, we have all the pieces. We have position, velocity, and acceleration. And they're all linked together by derivatives and integrals. We can finally see the complete, elegant architecture of motion.
So check this out. This is the kinematic engine. Think of it like a map. If you start with any one of these three, position, velocity, or acceleration, you can get to any of the others. You just move to the right by taking a derivative, or you move to the left by taking an integral. This simple map can describe any continuous motion in the entire universe.
And what is absolutely mind-blowing is that this simple engine works perfectly in 3 dimensions. To describe a really complex 3D flight path, you don't need some fancier, more complicated tool. You just break the motion down into 3 separate, simple one-dimensional problems. One for the x direction, one for y, and one for z. And you just solve each one by itself.
This approach reveals the hidden geometry of the world around us. I mean, think about throwing a ball. Horizontally, its speed stays pretty much constant. But vertically, it's constantly being accelerated downwards by gravity. And when you combine those 2 simple, independent motions, the kinematic engine shows that the ball's path will always trace the elegant curve of a perfect parabola.
And so we've come full circle, right back to the image from the very beginning. This complex, beautiful motion, which once seemed impossibly complicated, can now be perfectly described and even predicted. It's all thanks to the universal language of calculus.
And that leaves us with one final thought. Calculus gave us the language to finally see the hidden architecture of motion. So what other invisible patterns, what other hidden structures are shaping our world right now, just waiting for us to find the right language to bring them into view?